following thing. First thing, imagine we've got three components, 1, 2, and 3. Right, three different components, and we want to assemble them together. They may bolt together, or they may stick together, whatever it might be, we're going to assemble them. And let's imagine that component 1 has a dimension which is 10 plus or minus 0.1, that's its width. Component 2 is 20 plus or minus 0.2, and component 3 is 30 plus or minus 0.3. Right? We're going to assemble those together, and what we want to know is what the tolerance on this dimension ought to be. It's going to be 60 plus or minus something. Agreed? Yeah? Because it's 10 plus 20 plus 30. But what's the tolerance on that? Let's think about it. A number of assumptions we've got to think about is that the manufacturing processes are in statistical control. That is that we've got, when we manufacture something and we measure them, we get something like a distribution. Yeah? That is recognisably a distribution. Okay? That's the first thing, it's in statistical control. The processes are centred around a robust nominal value. So we've got a nominal value and we've got some variation to either side. And that the process capability is within the range plus or minus 3 sigma, just as we've discussed. So these are three assumptions. What is this tolerance going to be? Now you'll already be having some thoughts about that. What would you put on the drawing? Would you add them together like this? And say that the tolerance that you would put on your drawing is plus or minus, is 60 plus or minus 0.6. Is that what you'd put on your drawing? If I asked you to tolerance that part? Yeah? Is that what you would put on it, or not? You must have all done some tolerancing in your time, done a drawing of some kind. Is that what you put on it? Or are you thinking, if he's saying that, then there must be something wrong with it? Yeah, is it the reverse psychology at work? What would you put on it? I think your first instincts would be to do this, to add them together. Let's just jump back to the drawing and see what it's telling us. There you are. It's saying if this was 60 plus or minus 0.6, then that's saying that this dimension here could be 60.6, or it could be 59.4. Yeah, it would be within that range. Is that reasonable? It would mean that everything, like if this was 10.1, 20.2, and 30.3, that would be 60.6, wouldn't it? So everything would be potentially within that complete range. So at first hand, it looks to be sensible. However, and this is the however, there are three important influences on this. Component dimensions are first of all statistically distributed. Random assembly is assumed and is normal in high volume production. By random I mean that you've got a box of component 1, component 2, and you just one from each, assemble it, one from each. It's random. Okay, yeah? You asking a question, or
no, I'm just...
you're just making an observation? And the other thing is that the additive law of variances apply. Now there's somebody, you, who's asking, what do we do with these things? Well, we've got this thing called the additive law of variances, which we'll be talking more about. Basically it says sigma squared, that's the variance, of the assembly, is a summation of the variance of component 1, component 2, and component 3. That gives us the overall variance of the assembly. Now, the astute amongst you will be thinking, this is a bit like the variance of our process. Is the variance of our process the sum of the variances of the individual parts? Yeah? Although these are physical things, it can also be a process. So, knowing that this happens, does that change our thinking? So this is the picture that we've got here. Component 1, sorry about my little distributions, all got a bit crazy. This is a distribution for component 1. 2, about the nominal 20, and this is at about component 3. Of course, what will happen in reality, imagine that these are 3 boxes, and this are all the components in these boxes. And I go along and I think, okay, I'm going to put my hand into box 1, and let's imagine I pick out this component here on this distribution. And then I go into box 2, and I pick out this component on this distribution. And then component 3, and I pick out this one. None of these 3 are at the extremes, are they? None of them are this value at the end. They're all something else. In fact, when you look at this diagram, you realise that most of the components are not these black dots at the extremes. Most of them are something less than that. So you're putting a tolerance on your drawing that kind of assumes that every component is at the extreme. But they're not. There's only a few in all these thousands you've made that are at that extreme. Yet, you put a tolerance on a drawing to try and accommodate all of these components that are at the extreme. So we can't have that, can we? So, what we're saying is if we look at this, because plus or minus 3 sigma spans about 99.8% of all the parts we make, that the probability is 0.2 to the power 3, 0.008. That's the probability that we would pick out at random from each of these 3 boxes a component, each of these components at an extreme value. That is, say, 10.1, 20.2, 30.3. That's the probability of picking that out of that box. And yet we have put a tolerance on there to accommodate that situation. It's not right, is it? It's crazy. We're putting a bigger tolerance than we need to do. We actually might be able to have a smaller tolerance and maybe potentially a higher quality if we just think about this carefully. So let's jump on a little bit. So let's think about when we're doing this differently. Here's part 1. The standard deviation for this part is 0.2 divided by 6, because 0.2 is the total tolerance. Yeah, sigma is that's going to be divided by 6. So sigma is 0.033 for this. That's the distribution, the standard deviation of that distribution. We've got our standard law of variances equation. So we can say that the assembly standard deviation is the square root of component 1 standard deviation squared. We can do the same calculation for all the other components. This one becomes 0.66 squared, and the third one is 0.1 squared. So that tells me that the standard deviation of the assembly ought to be 0.128. If somebody was asking me, again, I think it was you, if we know the standard deviations, can we work out what the tolerances are? Well, this is an example of it, where we know what the standard deviation of the assembly has to be if we've got that variance in each of these 3 components. So, what do we do with that? Well, again, we know it's under plus or minus 3 sigma. So we're saying that virtually all the assemblies, the tolerances, all the assembly tolerances will fall within plus or minus 3 times this sigma, 0.128. So that tells us it would be 0.0384 for the tolerance on that particular assembly. So let's compare it. That's the tolerance you were going to put on the drawing if you had added up the tolerances. That's the tolerance you should put on the drawing. Look at the difference. It's about, well, 0.6 to almost 0.4. Significant difference. That's a much tighter tolerance. And you're achieving that tighter tolerance on that assembly without doing anything, aren't you? You're just making the parts to the quality that you make them to. But you're recognising it's a statistical decision. It's not deciding on the maximums. So what you end up with by putting that tolerance on is that you will get 99.8% or better of all the things you make falling within that tolerance in your assembly. And you don't need to put that bigger tolerance on it. And you'll you'll get that for free because you're making things to the right quality. So this little statistical thing on the dimensions of components can also be applied to the process that you're looking at. You can decide what that sigma, or work out what that sigma is going to be in order to make your process work correctly. I'm going to leave you to think about that. Okay? Any questions on that?
Yes, please.
Yeah.
Would you tell us how we would work it out for a process, or we would have to think about it, because I'm pretty sure it would not be the same as what you taught us for assembly.
It won't be exactly the same, no.
No, if, for example, for the piston, the diameter is pi d square, because
Yes.
the process is affected by the by the square of the diameter.
Yes.
So it cannot be the same. I cannot, I cannot add the tolerance for diameter into the process deviation.
Yes, correct. That's why, as I mentioned to you, we need to have something called the variance equation. That was the additive law of variances.
Right.
But we'll move on and you'll find that there's a slightly more complex solution to this. But this is getting you thinking about what's actually happening at these basic levels and how you can start to control them. Okay? So think about that again the next time you have to put a tolerance on something. What is the actual tolerance that should be there? What will actually be delivered? And a lot of students spend their time trying to work out, what tolerance have we put in? Actually, the tolerance will be given by how you manufacture. That will decide it, not you. That's how you've got to think about it. Now, what you're putting on the drawing is what the manufacturing process will deliver. And that's very different to thinking about what should I put on here. Now, you could do that thing in reverse if you want to think about that over the weekend, because I know you've probably got very little to do. Think about this, think about it in reverse. Let's imagine you had to have a particular tolerance on the assembly because it was going to fit into something. Then you could decide what's the individual tolerance required for the components. What do I then have to manufacture them to? And that then gives you the link between what the tolerance needs to be and what your manufacturing process needs to be able to do. The two things go together. Right, I'm going to call it a day there. You've got quite a bit to think about. Yeah, you're meeting each other maybe for the first time, so you've got a bit of a time socialising to do and get to know one another. So please, when you come along next week, be ready to start working in these groups. If there are people missing, if you get the chance to just prod them with something sharp, do that and get them to make sure they come along, right? There's one other thing before I finally shut up. Next week, I've got a visitor from a company in Aberdeen who works in the oil and gas industry and travels the world working in the oil and gas industry. And I was thinking it would be a good idea to get him to talk to some of the postgraduate students about how he got into the industry, what he does, and what the job prospects are in the oil and gas industry, both here and globally. Would that kind of talk you'd be interested in listening to?
Yes.
Yeah? So I was thinking about asking him to give the talk during the lunch break before this class next Friday. So it would maybe be between, say, I don't know, 1 o'clock and 2. Would that be something you'd like to attend? Would you be able to attend?
What company is it?
I can't remember the name of the company. I'll tell you when he comes along. It's gone. But he works globally, he works in Nigeria and various other places, working on projects there, offshore and onshore.
It's a big decision for the champions, but it's hitting
Next
about
Friday,
after lunch.
Immediately
next
before
Friday,
this
before
venture.
class.
In fact, I'll probably try and do it in this room if I can. We'll see. Is that something you're interested in? So if I emailed you to confirm before this Friday that you're going to do it, you can be here. If you can come along, that would be great. And I'll also try and get other students who come along together who you might be interested in. Okay?
Okay.
Great. So I'll see you next week. Thank you very much.